Hi, my name is Shahnawaz. In this lecture, we are going to study the contraction and extension of ideals. But before we proceed further, let us recall what we did in last lecture. In last lecture, we studied the radical of an ideal. So suppose I is any ideal of a ring A, then by radical of I denoted by R of I is actually all elements in A such that A power some positive integer is in I, where this n is bigger or equal to 1 and belongs to the ring of integers. Then we call this radical of we call this set the radical of I, and in last lecture we have seen that this radical is actually an ideal, and we did some exercises on radical of I. So this is by definition, so this radical of I is actually the inverse image under the canonical map pi inverse of the nil radical of A mod I. So this is what we have seen in last lecture. Now what we are going to prove in this lecture is this proposition, which states that the radical of I is actually the intersection of all prime ideals that contain I. So the radical of an ideal I in a ring A is the intersection of all prime ideals in A that contain I. Now let us prove this. So we know that this radical of I is actually the inverse image under the natural map, that is pi inverse of nil radical of A mod I, where this pi is the canonical projection from A to A mod I, and this n of AI is the nil radical of A mod I. But in last lecture we have seen that the nil radical of a ring A is actually the intersection of all prime ideals, where P is prime ideal in A. So this is already done in previous lectures. So we are going to use this result on this ring A mod I. So let P alpha bar, where this alpha is in lambda, be the collection of all prime ideals in A mod I. So these are the collection of prime ideals in A mod I. Then we know that this nil radical of A mod I is actually the intersection of these P alpha bars, these prime ideals, where this alpha is in lambda. I mean the null radical of A mod I is the intersection of all prime ideals in A mod I. So therefore now we are going to use this. So therefore radical of I, which is actually the inverse image of null radical of A mod I, which is further equal to the inverse image of intersection of all prime ideals in A mod I. So this alpha is in lambda. Note that this pi is the surjection, so this is same as, so this is equal to intersection of P alpha, I mean this is the intersection of inverse image of P alpha bar, where this alpha is in lambda. So since we know there is a one-to-one correspondence between the ideals of A mod I and the ideals of A. In particular, there is a one-to-one correspondence between the prime ideals of A mod I and the ideals of A that contain I, and those ideals of A are also prime, because we know that the inverse image of a prime idol is prime idol, i.e. the ring homomorphism pulls back prime ideals to prime ideals. So hence if a P alpha bar is an idol here, then corresponding to P alpha bar we have a prime idol P alpha here that contain I, because there is one-to-one correspondence between the ideals of A mod I and the ideals of A that contain I. So this P alpha surely contains the ideal I, and this P alpha is also prime in A, because this P alpha is actually the inverse image of this P alpha bar, while P alpha bar is prime in A. So let us write this down here. Since inverse image of a prime ideal under a ring homomorphism is a prime ideal, therefore pi inverse of P alpha bar is prime ideal in A. Also pi inverse of P alpha bar, so let us denote this. So pi inverse P alpha bar contain the ideal I of A by this is follows by correspondence theorem. So let us write this down here. So let us write this down by correspondence theorem. So let us write and mark this as expression star. So then star shows that a radical of I is intersection of, since each of pi inverse P alpha bar is prime ideal, so this is intersection of I mean the prime ideals in this is the intersection of prime ideals in A that contain that contain I, because this is a prime ideal in A and it contains I. So hence we are done in this case. Now there is another small result. So we have this proposition. So let D be the set of zero divisors in a ring A. Then we know that this D is an ideal. So the result says then D is same as it is radical, which is equal to the, by definition it is, since D is by definition the union of annihilators of non-zero elements in A. So let us prove this. So proof. So we know that this D is actually the union of annihilators of non-zero elements in A. So this X is a non-zero element in A. Therefore we have to prove, therefore we need to show that D is same as it is radical. Note that D is always contained in this radical, because we know I is always contained in the radical of I. So it suffices to prove, that D contains a radical of D, since this containment is trivial. So since D is contained in a radical of D. So now to prove this containment, let X belongs to rad of D. Then there exists, say, some n bigger or equal to 1 such that x to the power n is in D, i.e. x to the power n is a zero divisor. That means there exists some non-zero y in A such that the product of x to the power n times y is 0, or x dot, I mean this element x to the power n minus 1 times y is 0. This proves this x is a zero divisor. So hence x is a zero divisor. Therefore D contains a radical of D. Hence D is same as it is radical. Now let us move towards the contraction and extension of an ideal. So we have this definition here. So let f from A to B be a ring homomorphism. So this is a ring homomorphism. Let I and J be ideals in A and B respectively. Then we define the contraction, or we define let us first define the contraction. So we have, this is over ring A and this is over ring B. So this is ring B, this is the ideal I, this is the ideal J here. Well, now we know that a ring homomorphism pulls back ideals to ideals, but the other way around is not true. So the contraction J to the C stands for contraction. So the contraction of J with respect to this ring homomorphism F. So let us mention this with respect to F is defined as, so this J contracted is actually the inverse image of J, which is by definition all those elements in ring A whose image is in J. So we know that this inverse image is an ideal. So this contracted ideal is actually an ideal. So let us write this down here. So this is an ideal defined as this thing. Now if we have ideal in I, then its image need not be an ideal in B unless this F is a surjection. So let us define now the contraction. So the contraction, sorry, the extension, I mean the extension of I sub E, so of I is an ideal in B, this is ideal in A, defined as, so this I into the E is defined as the ideal generated by the image of I. So which is same as all finite sums say Bi f of Ai, where this sum is a finite sum. Otherwise this sum, if this is an infinite sum, this won't make any sense. So this Bi is in B, Ai is in A, and this n is a non, this is a positive integer. So note that this is an ideal in A which contain this set f of I. So this is defined as the extension of I. So one should remember here that so if we look at the so if we look at the ideal J and J contraction and the ideal I, and it is extension. Now this is our ideal I, this is our ideal J. Now if we look at it is inverse image, so this is F inverse J, which is actually J complement. Now if we look at the image of J complement, which is an ideal and F of J, then note that not F of J, I mean if we look at the ideal J and it is image, so this is the ideal J complement and this is J. So if F is not surjective, then there is some part of J which do not have pre-image. So if we look at the F of J complement, that is this shaded part. That means this f of j complement is always contained in j. That is why j complement is called the contraction of j. And if we look at I and I extended, and if we look at the image of I and it is extension, then this image is always contained in the extension of this ideal. Note that this we have equality here if f is surjection, and similarly we have equality here if f is surjection. So this is a small observation. So this is what we call the extension and contraction of an ideal. But we have forgot to give examples of radicals. So I think first I should give examples of radicals of an ideal. For example, so this is the examples. So let A be the ring of integers and I be the ideal generated by say 20. So this is 20z, or the ideal generated by 20. Then we know the radical of I is actually the intersection of prime ideals in A that contain I. P must contain the ideal I and is prime in Z. Now we have to look at all prime ideals of Z that contain 20z. So the ideal generated by 2 is actually a prime ideal which contain 20z. Similarly, the ideal generated by 5 is again a prime ideal that contain the 20z. So both these ideals contain 20z. Now these are the only prime ideals that contain 20z. So this radical of I is actually their intersection. Now we know that the intersection of two ideals is the ideal generated by the LCM of 2 and 5, because these are principal ideals. So this is the ideal generated by LCM of 2 and 5. So this is actually the ideal generated by 20. Sorry, I mean the ideal generated by 10. So this is an example here. So one can look at different examples as well. Now let us go back to extensions and contractions. Again we have, so note that so let us give an example here. So let A be the ring of integers, B be the ring of rationals, which is also a field, and F from Z to Q be the identity embedding. I mean F takes Z to the copy of Z in Q. So be the identity embedding. Then one should note here, so let nz I is equal to nz be any ideal in and be any non-zero ideal, I mean be any non-zero ideal in say Z. Now I be and this F being the identity embedding, this nz is not going to be this nz is not carried out to the zero ideal of Q, but Q being a field, it has only two ideals, i.e. the zero ideal and the Q itself. So then if we look at the extension of I in Q, so that is going to be an ideal in Q, but this I extension is also a non-zero ideal because this I is non-zero ideal. So its image in Q is a non-zero ideal, so it has to be it must be Q itself, because Q has just two ideals, i.e. the zero ideal and Q itself. So now there is this question, one should see here that, so I mean the contraction always preserves the primeness of an ideal, however the extension does not preserve the primeness. The reason is, so if we have ring A here and we have ring B here, so there is this homomorphism F between these two rings. So suppose we have a prime ideal here, say P, then if we look at its inverse image, which is actually the contraction of P, then this inverse image is always a prime ideal. The contraction preserves the primeness of an ideal. However, this is not the case with the extension. For example, if we have a prime ideal here, so suppose this is a prime ideal, suppose Q. Now if we look at the ideal generated by the image of Q, which is the Q extension, this ideal need not be a prime ideal in B, i.e. the extension does not preserve the primeness of an ideal. We'll see some examples in a bit that this extension does not preserve the primeness. So let us make this observation here. So this is the first observation. The contraction preserves the primeness of an ideal. The reason is that the inverse image of any prime ideal is a prime ideal under a ring homomorphism. So the second observation is the extension does not preserve the primeness. I mean, it may not preserve, the extension may not preserve the primeness of an ideal. So this is true. Now let us give some examples to support the second argument, i.e. the extension may not preserve the primeness of an ideal. So let us look at the ring Z of integers. So this is the example. So let I from Z, which is a ring of integers, to Zi, which is a ring of Gaussian integers which contain elements of the form a plus bi, where this a and b are integers and this I is actually the square root of -1. So this is a ring, and this is called the ring of Gaussian integers. So we'll let this I to be the identity embedding, so be the identity embedding. Now any prime ideal in Z will look like pz, i.e. the ideal generated by P, where P is some prime ideal. So let I be any prime ideal in Z. So then this I will look like, so then I is P times Z, which is same as the ideal generated by P, where this P is a prime number. Now if we look at the extension of pz, so this extension of pz is actually the ideal generated by I of pz. So this is the ideal generated by I of pz. Now this is same as the ideal generated by pz in the ring of Gaussian integers. So this is the ideal generated by the ring of Gaussian integers. So that is it contains elements of the form P times alpha, while alpha is in the ring of Gaussian integers. So this is same as P times Zi. There is no distinction between these two sets. So this is just extension. Now there is this question: this pz is prime in the ring of integers. Now the question is whether this P of Zi is a prime ideal in Zi or not, and the question is no, it need not be, because so note that P of Zi need not be prime ideal in the ring of Gaussian integers. For example, if P is 2, then we have, so let P is equal to 2. So then pz extension is actually the P times the ideal generated by P in the ring of Gaussian integers. So but P is 2 here, so this is 2 times Z is same as this ideal here. But if we look at the element 2 in Zi and the element 1 plus I square, which is 2i, so the ideal generated by 2 in the Gaussian integers is same as ideal generated by 2i in the ring of Gaussian integers, which is same as the ideal generated by the element 1 plus I square times the ring of Gaussian integers. Note that this element is not prime in the ring of Gaussian integers, since the ring of Gaussian integers is ED, i.e. the Euclidean domain, hence it is a unique factorization domain, and in a unique factorization domain there is no distinction between the primes and irreducibles. Now one can note here this 1 plus I square is not this is reducible, hence it is not irreducible, hence it is not a prime. So the ideal generated by this 1 plus I square is not prime ideal in the ring of Gaussian integers. This implies the ideal generated by 2 in the ring of Gaussian integers is not prime ideal. So this is same as 1 plus I square times Zi. which is not prime ideal in Zi, since 1 plus I square is not irreducible and hence not a prime. So knowing that this Zi is the Euclidean domain, so we must have a function which we call the Euclidean function, so which we call the Euclidean function, or sometimes a norm, which is a function f from the ring of Gaussian integers to the non-negative integers. So here this function is given as, so this f of a plus bi is actually a square plus b square. So this is the norm on the Euclidean the ring of Gaussian integers. Now there is this question, which prime ideals if we have to exhibit the ideals in Z whose prime ideal is in Z whose extensions also are prime, then what is the way to exhibit those ideals in Zi? Now suppose so this is item first. Suppose p is a prime in integers. So suppose p is prime numbers. So suppose p is a prime number in Z such that p is congruent to 1 mod 4, i.e. p leaves a remainder 1 when we divide it by 4. Then the Fermat's theorem on sum of two squares says that this p can be expressed as sum of two squares for some integers a and b, i.e. if we look at 13, so 13 is a prime number which leaves remainder 1 when divided by 4. So that means the 13 can be expressed as sum of two squares, i.e. it is sum of 2 square plus sum of 3 square. Now let us look. So now this p is a prime of this form, then pz is obviously a prime ideal in the ring of integers. Then its extension is actually p times the ring of Gaussian integers. Now this p is also the sum of two squares. So here this can be expressed as a plus ib and a minus ib. So we can write this as a square plus b square times zi, which is same as a plus ib times a minus ib times the zi. That means this p is not irreducible in zi, hence it is not a prime. So this extension is also not a prime ideal in zi. So hence p of z extension is not prime ideal in zi, since this p is not reducible, i.e. p is a plus ib times a minus ib. Now what are the prime numbers in the ring of integers whose extension is also a prime idle in the ring of Gaussian integers. Now that means we have to look at the primes in the ring of Gaussian integers. So there is a result that if P is congruent to 3 mod 4, where P belongs to Z is a prime, then P is a prime number in